continue our discussion on transfer functions. Transfer functions. Yesterday we have considered a single input single output system, and we have derived the transfer function for that SISO system. So, for a SISO system, the process involves single input and single output. Suppose this is a process, this is the input to the process and this is the output of the process. We have represented the input by f t and output by y t, fine, and the process is modeled by an nth order linear or linearized nonlinear equation. So, we considered in the last class the nth order model represented by a n d n y d t n plus a n minus 1 d n minus y d t n minus 1, like this, a 1 d y d t plus a naught y equals to b f t, fine. A and b, these are constant coefficients, a and b, these are constant coefficients, and both output and input, these are deviation variables, fine. In the next step, we took Laplace transform of the process model, and finally, we got the expression in S domain, that is like this, y s divided by f s equal to b divided by a n s to the power n plus a n minus 1 s to the power n minus 1 a 1 s plus a naught, which is basically the transfer function represented by G s, fine. Then in the next step, we made the block diagram. Block diagram is like this, G s is representing the process, the input to that process in Laplace domain is f bar s and output is y bar s. This is the block diagram for the SISO system. Now, today we will consider one multi input single output system, and we will try to derive the transfer function for that process. Today we will derive the transfer function for a multi input single output system, MISO, multi input single output system. So, the process we can represent by this. Suppose the process, this is the process, this is one input represented by f 1 t, another input we will represent by f 2 t, fine, and single output, that is y t. So, this is the representation of a multi input single output system. So, next we have to consider the model for this process. So, we will represent the process by this equation A n d n y d t n plus n minus 1 d n minus y d t n minus 1 like this A 1 d y d t plus A naught y, and right hand side includes two input variables, one is B 1 f 1 t and another one is B 2 f 2 t. Fine. The process model is quite similar with that of the seesaw system, only new addition is the input variable. In the previous case we had two input variables, here one input variable. Fine. So, next we have to take the Laplace transform. If we take the Laplace transform and if we rearrange, then we will get the expression like this B 1 A n s to the power n A n minus 1 s to the power n minus 1 A n s plus A naught multiplied by f 1 bar s. Another expression will be B 2 divided by A n s to the power n A n minus 1 s to the power n minus 1 A 1 s plus A naught f 2 bar s. Fine. In this discussion you remember that y and f both are the deviation variables. So, this is the representation in S domain of the linear model or linearized nonlinear model. So, we can write this equation in this form y bar s equal to z 1 s f 1 bar s plus z 2 s f 2 bar s. Fine. We can rearrange the equation, I mean the Laplace the equation in Laplace domain by this equation, where this part represents z 1 and this one is z 2. Fine. In the next step we need to develop the block diagram. What will be the block diagram of this system? So, we have basically two transfer functions, one is z 1, another one is z 2. Two inputs in Laplace domain, one is f 1 s, another one is f 2 s, and single output, that is y s. So, one block for z 1, input to this g 1 is f 1 bar s. Another block we need to use for transfer function g 2. Input to this block is f 2 bar s. Fine. Now, the output of these two blocks we need to add. Suppose we are using this symbol to add these two signals, one is this one, another one is this one. Fine. So, this output is basically f 1 g 1 and this is f 2 z 2. So, f 1 g 1 plus f 2 z 2, that is nothing but Ys, agree? F1 multiplied by G1, that is this signal, and this signal is basically F2 multiplied by G2. So, if we add these two, we get Ys, fine. So, this is the block diagram, of the multiple input single output example, fine. Now, if we consider n number of input variables, but a single output variable, what will be the block diagram for that? If we consider n number of input variables f1, f2 up to fn, and if we consider only one output variable y, what will be the block diagram that you draw? So, this is G1, input to this G1 is F1, next one is G2, input to G2 is F2. Like this way, last term will be, suppose last transfer function is suppose GNS, input to this is MFNS. By adding all these outputs, we get Ys, fine. So, this is for several inputs and single output. This is the block diagram with block diagram for processes with several inputs and one output or single output, fine. Now, to find the transfer function of a process, of a nonlinear process, we need to note two important points. One is, if the model is nonlinear, we need to linearize that equation. This is the first point. Second point is, we need to represent the linearized equation in terms of deviation variables, fine. So, these are two important points which we need to follow to derive the transfer function. One is, if the process model is nonlinear, we need to linearize that equation. If that is linear, it is fine. Second point is, we need to represent the linearized equation in terms of deviation variables. Another question comes, that is, what is the use of this transfer function? What is the use of this transfer function? Okay, we will consider one single input single output system. So, for a seesaw system, we consider one process and input to this process is Ft, output to this process is Yt, fine. For this seesaw system, the block diagram is Gs, input is F bar s, output is Y bar s, fine. Now, Gs is known to us. I mean, if we have the process model, we can easily derive the transfer function for that process. So, Gs is derived, I mean Gs is known to us. So, Gs is suppose given. Now, what we can do? We can give a change in input variable. Ultimate answer is to observe the process dynamics, we use the transfer function. Fine. By the use of transfer function, we know the transient behavior or dynamic behavior of a process. But how we can know that? We have the process initially at steady state. Fine. Now, we are introducing some change in input variable. Fine. Change in input variable. We are introducing some change in input variable, and that is represented by f t. We are introducing some change in f t. Then we can easily transform this f t to f s by taking Laplace transform. Say for example, if we introduce a step change with magnitude a, suppose this is the step change with magnitude a, we can change it in S domain. How much that will be? A by S. Fine. In the next step, we can determine y bar s. How we can determine y bar s? Y bar s is Gs f bar s. Fine. So, it is straightforward to determine y bar s. Now, we need to take the inverse of Laplace transform, so that we get y t. If we can determine y s, then we can get y t by taking inverse of Laplace transform. Fine. So, we have a particular process, we are introducing some change in input variable in terms of f t. Now, we can change to that input in S domain represented by f bar s. In the next step, we can calculate y bar s, because y bar s is equal to G s f bar s. Fine. Then by taking inverse of Laplace transform, we can know y t. So, if we give a change in input variable f t, we can know the transient behavior of that process in terms of y t. So, that is the use of transfer function. Fine. Now, we will consider some chemical engineering examples, and we will try to find the transfer functions. First, we will consider a simple example, that is liquid tank system. So, we will derive the transfer function of a liquid tank system. We will derive the transfer function of a liquid tank system. So, this is the schematic of a liquid tank system. A liquid is entering at a flow rate of F I, and the output is coming out at a flow rate of F naught. The liquid height is H, cross sectional area of the tank is suppose A. Fine, this is a schematic of a liquid tank system. F I and F naught both are in terms of volumetric flow rate. So, F I and F naught are the volumetric flow rate. I hope we have considered this example previously. Fine. So, we will discuss stepwise. In the first step, we need to develop the model. In the first step, we need to develop the model. This is the first step. The model should be linear or linearized nonlinear model. If the model is linear, it is fine. If the model is nonlinear, we have to linearize that using Taylor series. So, what is the model of this system? I mean, what is the modeling equation? If dH dt equal to f I minus f naught by assuming the liquid density constant. So, this is the modeling equation for the example liquid tank system. In step 2, we need to construct the model in terms of deviation variables. In terms of deviation variables, fine. So, to construct the model in terms of deviation variables, we have to consider the model at steady state. So, what will be the modeling equation at steady state condition? At steady state, the modeling equation becomes f I s minus f naught s. We have just added suffix s to represent the steady state, fine. Anyway, this model is the linear equation or nonlinear equation? This is the linear equation. So, there is no need of linearization. So, this is the equation, modeling equation at steady state condition. So, how we can represent the modeling equation in terms of deviation variable? We need to subtract this steady state equation from this dynamic equation. So, the model in terms of deviation variables has this form: a dh prime dt equals to f I prime minus f naught prime, where f I prime is f I minus f I s, f naught prime is f naught minus f naught s, and h prime is h minus h s. So, this is the mathematical model in terms of deviation variables. In step 3, we need to take Laplace transform, fine, and we need to derive the transfer function. So, in step 3 we will determine the transfer function. In step 3 we need to determine the transfer function. So, for that we have to take the Laplace transform. If we take the Laplace transform, we get A s h bar prime s equal to f I bar prime s minus f naught bar prime s, fine. This is the representation of the model in S domain. Now, if we rearrange this equation, we get h bar prime s equal to 1 by A s f I bar prime s minus 1 by A s f naught bar prime s, fine. So, this is the equation which we got finally in Laplace domain or S domain. In the next step, we need to make the block diagram based on this equation. So, in step 4 we need to make the block diagram. Fine. Can you make the block diagram based on this equation? So, one transfer function is 1 by A s, another transfer function is 1 by A s you can consider, or you can consider minus 1 by A s. Fine. So, the block diagram will be 1 by A s, input to this block is f I bar prime s, another transfer function is 1 by A s, input is f naught bar prime s, so we will use here positive sign and here negative sign. Output is h bar prime s. Fine. We are just considering 1 by A s f I bar prime s minus 1 by A s f naught bar prime s equals to h bar s. Why negative sign is there? Because f naught is the output and f I is the input. So, we can say that f naught is the negative input. Fine. Or you can do one thing, if you want to consider minus 1 by A s as the transfer function, then we can get this block diagram f I bar prime s and another transfer function is minus 1 by A s f naught bar prime s. We are adding both of these output and we can get y bar s. Fine. This block diagram also we can get. In the next we will consider another example, that is a Cstr. So, we will derive the transfer function of an isothermal Cstr. We will derive the transfer function of an isothermal Cstr. Previously, we have considered one Cstr. I mean, we have developed the model structure of a Cstr previously, and the model structure of that Cstr includes 3 equations. Can you remember these 3 equations? One is based on mass balance, I mean total mass balance. One equation we got based on total mass balance. Second equation we got based on component mass balance, and another equation, I mean third equation we got based on energy balance. Fine. Now, isothermal means constant temperature. So, for the case of isothermal Cstr, the operation, I mean the reactor operates at constant temperature. So, there is no variation of temperature. If that is the case, then we have considered one Cstr and we derived modeling equations based on these 3 balances. So, what is that Cstr? Yes, that is a non-isothermal Cstr, because temperature varies in that Cstr with time. So, the Cstr which we have modeled earlier, that is the non-isothermal Cstr. Non-isothermal Cstr. So, for a non-isothermal Cstr, the energy balance equation we usually derive. Now, here we will consider the isothermal Cstr. Isothermal Cstr, total mass balance. There will not be any total mass balance equation. How we can avoid this? If we assume the reaction mixture volume constant. I mean, if we consider the volume of the reaction mixture constant, in that case we can avoid total mass balance equation. So, we are assuming that. Second is component mass balance. Component mass balance we will consider, fine. And third one is energy balance. Energy balance does not exist for isothermal case. So, presently we will consider the we are considering the isothermal Cstr that includes only the component mass balance equation, fine. Now, the schematic representation of an isothermal Cstr is like this. Inlet flow rate is Fi, concentration is Cai. The output is coming out with a flow rate of F and a concentration of Ca. So, the concentration in the vessel is also Ca, and we will assume the volume is V. Since there is no variation of temperature, so there is no need of any external heating or cooling medium, fine. So, what will be the component balance equation then? Fi and F both are volumetric flow rates. This is a schematic representation of an isothermal reactor. What will be the component balance equation? Component mass balance equation. Previously we got this equation, dCA dt equal to Fi divided by V Cai minus Ca minus K naught exponential of minus ERT into Ca. This equation we derived for non-isothermal Cstr. How we can represent this equation for the case of isothermal Cstr? See, in this is basically K, is not it? This whole term is basically K, and in this term you see temperature is there, since the case is non-isothermal. If we consider the isothermal Cstr, the temperature is constant. So, this whole term becomes constant. So, we can rewrite this equation for the case of isothermal CAI minus CA minus KCA. For the case of isothermal, there is no variation of temperature, that is why this whole term becomes constant, and that we are representing by K. So, this is the modeling equation for the isothermal Cstr. Now, we need to represent this equation in terms of deviation variables. Anyway, before that we can simplify this equation like this. This is our modeling equation, dCA dt equals to Fi divided by V Ci minus Ca into Kca. Now, we can write this equation in this way: dCA dt plus Fi divided by V plus K multiplied by Ca equal to Fi divided by V multiplied by Cai. Fine. It gives dCA dt plus 1 by tau plus K multiplied by Ca equal to 1 by tau Cai, where tau is V divided by Fi. Tau is V divided by Fi. Fine. Next, we will represent this equation in terms of deviation variables to find the transfer function. You directly write the equation in terms of deviation variables. Write the equation in terms of deviation or perturbation variables. dCA prime dt plus 1 by tau plus K multiplied by Ca prime equal to 1 by tau Ci prime. This will be the model equation in terms of deviation variables, where Ca prime is Ca minus Cas and Cai prime is Cai minus Cai s. To get the transfer function, we need to take Laplace transform. Take Laplace transform of this equation. If we take the Laplace transform of this equation, we get S Ca bar prime S plus 1 by tau plus K Ca bar prime S equal to 1 by tau Cai bar prime S. Fine. Now, the transfer function represented by Gs equal to output divided by input equal to 1 by tau S plus K plus 1 by tau. This is the final representation of the transfer function for the example isothermal Cstr. Fine. This is the transfer function. Now, the block diagram is quite straightforward. We can directly write Gs equal to 1 by tau divided by S plus K plus 1 by tau. Input is Cai bar S, output is C A bar prime S. Fine. So, this block diagram is represented in terms of concentration, not in terms of flow rates, because we have already assumed the volume of the reactor is constant. So, this is the input concentration CAI and this is the output concentration. So, this is the block diagram for the example Cstr. Now, so far we have discussed the transfer function of single output, although we have considered multiple inputs, but our discussion is restricted to the single output. So, in the next we will discuss with the consideration of multiple outputs. Fine. So, we will consider multiple input and multiple output systems. So, transfer function of a multi input multi output system. Now, the process we will represent in this way. This is the process. Suppose one input is F1, another input is F2, they are in time domain, and we will consider two outputs, one is Y1, another one is Y2. Fine. So, in this MIMO system, I mean multiple input multiple output system, basically we are considering 2 by 2 system, 2 inputs 2 output. Fine. Now, first we need to write the input output model for this process. So, input output model is dy1 dt equal to A11 y1 plus A12 y2 plus B11 f1 plus B12 f2. This is a linear equation, and this equation is representing the variation of y1. Fine. Similarly, for the second output y2, we have the linear model represented by this equation dy2 dt equal to A21 y1 plus A22 y2 plus B21 f1 plus B22 f2. So, this is the model of the 2 by 2 system, I mean MIMO system. We can represent these two modeling equations in matrix form, and that is represented in this way, equal to A11 A12 A21 A22 Y1 Y2, and another matrix for input B11 B12 B21 B22 multiplied by F1 F2. Just we have represented these two modeling equations in this matrix form. Now, here y1 and y2 both are perturbation variables or deviation variables. So, y1 and y2 both are deviation variables. Fine. Now, if we take the Laplace transform of these two equations and if we rearrange, we get finally the equations which I am writing next. I am writing the final expressions. So, if we take Laplace transform, taking Laplace transform and rearranging, we get y1 bar s equal to s minus a22 b11 plus a12 b21 divided by Ps. Ps is a polynomial. We will write the expression for Ps later. So, this is the first right hand term and another term related to F2, that is S minus A22 B12 plus A12 B22 divided by Ps multiplied by F2 bar S. This is the final expression for y1. Similar expression for another output y2 we get, that is y2s equal to s minus a11 b21 plus a21 b11 divided by Ps F1s plus s minus a11 b22 plus a21 b12 divided by Ps F2 bar s. Fine. These are the two expressions, and the expression for the characteristics polynomial Ps is like this. The Ps is the characteristics polynomial represented by a11 a22s minus a12 a21 minus a11 a22. This Ps is the characteristic polynomial. Fine. Now, you see the output is multiplied by output equal to one transfer function multiplied by first input variable, another transfer function multiplied by second input variable. Similarly, for the case of second output, another one transfer function multiplied by first input variable, second transfer function multiplied by second input variable. So, we can write y1 s equal to g11 s f1 bar s plus g12 s f2 bar s. Similarly, if y2 bar s equal to g21 s f1 bar s plus g22 s f2 bar s. So, we can say that this term is basically g11, This is another transfer function related to first output, that is Z12. This transfer function is involved with Y2, that is Z21, and this is Z22. Fine. So, 4 transfer functions are involved, and the final expressions we have written here, and we can represent them in matrix form. So, if we represent them in matrix form, we will get y1 bar s, y2 bar s equal to z11, z12, z21, z22. Another matrix is for 2 input variables f1 and f2. Fine. So, this is about the derivation of transfer function for the MIMO system. In the next step, we need to make the block diagram. What will be the block diagram for this system? See, there are 4 transfer functions. One is G11, second one is suppose Z21, third one is Z12, and fourth one is Z22. Fine. Basically, the transfer function G has 2 suffix, one is I, another one is J. I represents output and another suffix J represents input. Fine. So, this is the nomenclature of the transfer function. So, G11, this first one means output. So, this is the output is y1, second suffix 1, that indicates the input and first input. Agree? Similarly, for the last transfer function, first suffix 2 indicates the output. So, output will be y2, second suffix 2 that indicates input. Second input is basically f2 bar s. So, how we can add the input and output streams with this G21? You see G21 first suffix is 2. So, output second output. So, this is the second output. Second suffix indicates the input, that is first input, that means F1. So, we will add F1. Similarly, for G12 first suffix is 1, that means Y1. And second suffix is 2, that indicates second input, that means F2. Fine. So, this is the block diagram of the multi input multi output system. So, this is the block diagram of a multi input multi output system. Okay. In the next class, we will discuss about the quantitative analysis of this transfer function. Thank you.